Hello and welcome to the usage manual of Rhino rotor blade. So my name is Felix Frischmann from FFR Engineering. Also check out ffrengineering.com for further information. We are a company from Munich, and in this video you will see how to use one of our software, which is basically an extension to Rhino, the famous freeform CID system. In this video I want to show you how to use our software, what is it doing, how can it help you, and give you some idea on how to exploit the extension for your purposes. There is also another video where you will find out how to basically install the software. There is no real installation process. Nevertheless, there are some little things you have to adjust to use our software, which is Python based. And this video you will also find in the link below in the comments and also on our webpage, where you find all necessary further information on this and other of our on also other softwares which we have. Yes, so let's come back to a Rhino rotor blade. As I said, this is a Python code. It's actually an object-oriented Python code with modules and real data structures. There are mainly three generators at the moment, a so-called cross-section profile generator, mainly for NACA profiles. You should be familiar with the term NACA. This is basically the profiles used for many wing shapes. And out of those are also wings and rotors possible to be generated using our extension. So this is built up hierarchically, so that NACA profiles are basically consisting of two curves, an upper and a lower curve, and they themselves are built from sample points. That's the standard way how to build the NACA profiles. And then those cross sections or airfoil cross sections can be assembled to form a wing model. This is the wing generator. And then there's a third generator, the rotor generator, to take those wings and bring them together in form of a rotor, including also a hub. You can also see this here on the slide. And all these slides are also provided to you if you download the folder with the extension. We will have later a look at it. But here you already see there are basically three steps. There's the step where you have the NACA profile generator, and then you can assemble them here to a set of cross sections forming a wing model, and then if you assemble those wings and add a hub in the middle, you have a rotor model. That's basically the idea of the extension. And yeah, let's go to the basic NACA airfoil profile generator. It's not necessary that those are NACA profiles. You will see if you look at the code, you can basically also find some other things like circular cross sections. You can extend it by your own ideas, but of course the main purpose of this extension was to have NACA profiles, and at the moment there are 4-digit series and 5-digit series provided for you. So these are terms from the NACA world for different series, how to generate the cross section, the airfoil cross sections. And at the moment you have those twos and also circular cross sections. You can extend that, and we also plan to extend in the future the set of provided cross sections by more flexible things and more maybe different cross section possibilities. But nevertheless, at the moment there are those options available already, and you will see that you can use them to generate some nice wing and also rotor models. If you use this cross-section generator, we'll have a look at that later in the code itself, then you will see that if you generate only one airfoil cross-section, that it will be consisting of an upper and lower curve to form this airfoil cross sections. And when you generate it, there are some arguments like a length parameter and a thickness parameter. There might be some more depending on your digit series, but basically and most importantly is the length and the thickness parameter. The length for the chord length, and the thickness, which is also basically defining the name of the NACA airfoil, if you might know it. One important thing is that we work here in the Rhinoceros CID system, of course, as you will see in a second. And in this, you consistently work with coordinate transformations and construction planes. Some people who are more familiar with products like NACA or I don't know, Inventor, they might be more used to the sketch-based approach on how to draw. Here in Rhino it's different, you have a real freeform system, nevertheless you have construction planes, so everything is designed on the construction plane unless you define it differently. And the same holds here. What we do is that we basically give basic local coordinate system to the airfoils, and you can change that. We call this transformation, so you can apply a custom transformation if you want to have this airfoil here in a different location in space, but you have to actively do that. If you don't do that, you have a default coordinate system where this will be drawn, and everything will be with respect to this sketch origin point or the tip point of the airfoil. And yeah, then you have this coordinate system. Here you see a picture, and you can also see it in the example 1, which we have a look at, that you can apply those transformations to transform such an airfoil in a different construction plane. So if you look at it mathematically in a different local coordinate system. And here we provide some utilities to make that more or less smoothly for you. And you will see that in the code itself. Let's jump to the wings. So the wings are, as I said, consisting of cross sections. So they're an assembly of cross sections. And there are some basic arguments also for the wing generation, like the wing length and again some wing transformation. Let's have a look at that in a second. But yeah, important is that you have here such a wing model where you consequently add some of the cross sections after each other, and then of course you can define from those cross sections a wing by sweeping along this cross sections to form a surface model. I guess this is what you want to have if you make some, for example, finite element analysis or something else. So you need a surface model, maybe even a solid model, but a start for that is a surface model, since Rhino is a BREP modeler, and thus you produce a model using here different cross sections. Of course, then it's important here that you make something sensible by adding the cross section. So of course you can make something not valid here. We simply assume that you as an engineer have of course the right approach, since you might also be working with Rhino a lot, to do something sensible, and the script will help you with that. So here we have the wing longitudinal direction, and we call it later the X position along the wing. And we also have the wing root point here again, which is here in the tip of the basically first cross section added. And then we have again those transformations. So similar to the airfoils, if you look at them separately, of course the same holds for the wing in total. We can apply on the generation of a wing instance. We can apply a custom transformation to bring the entire wing in some local coordinate system. And by doing that, this transformation will be inherited by all the airfoil cross sections you add later in the code, and we'll have a look at it. So basically we have to make this step only once. This is a Python code, and you will see it later, which is quite flexible. You can come to the same point by different means, of course. And since it's open source, you can also extend it the way you want. Here I just show the process in the way as it was intended by me as the author of the library, and yes, and some of the convenience tools to do that. And here the convenience is that you can only apply the transformation once, and then it will be added to all the airfoils itself. Again, on the adding an airfoil cross section to the wing model, which you will see later. Yeah, and this is here described, but we will have a look in the code. Basically, I only want to point your attention to this add profile. This is a command from the source code where you add one, I'll go jump back here, where you add, for example, here this cross section to the wing. Of course, now it's important that you add them after each other according to their position on the longitudinal wing direction. This is what you will have to do. And here I have already some pictures of those local transformations. What is that? So, as I said, when I will jump back here, when we make an instance of the wing, you give them a basic transformation. This basically defines the basic position of the wing in space. But now you also add, again with this add profile command, one of those cross section to your wing. And while doing that, you might want to have some change of this position, some local change of this position with respect to the root wing point. So assume you want this wing to have some kind of a bend here, and you will see it on the pictures. And then each of those cross sections which you have to be added with respect to the base point or base cross section with some either angle or with some translation. And this is exactly what we do when we apply here this local translations and also rotations to the cross sections of the wing. And you see here the pictures which will help you to understand in which direction basically you apply those transformations or rotations. So this is a vector of 3 values. Actually, you don't see a picture here for the third value, because this one is the one, and you will see it in the code, which you kind of always have to use, because this third value will define the position on the longitudinal direction of the wing where you're at your profile. So this is the first value here. This one has to be always given to make a valid wing model, as I said, because those cross sections have to be added in the order with respect to their position along the wing model. Now you might ask, this process could be automized. Yeah, you're right. Of course, if you know the wing length and if you know how many profiles you want to add, then you have here the position, the X position along the longitudinal direction. Nevertheless, at the moment, this is not done for you, so you still have to simply add that. That's very simple. You can have a look at the sample codes provided with the software. And we do that because some people might want to play around a bit here. So maybe at the beginning, where you have a bigger change of the geometry, you might want to have a closer network of the added cross section, and maybe in the back you want to have more space between the cross sections. This is why we give you the flexibility. But then there are the first 2 values in this vector here, and for example the first value gives you the possibility to add some in-plane translation. So in this picture we added something increasing with the distance from the root, and you see like that here the deformed orange shape, that you can produce a shape going in this direction, in this in-wing chord length direction. And if you play around with the second parameter, you apply something going out of the wing plane. And then there are some rotation values, for example the wing skews. I will start actually with this value here, the third value. Again, it's some vector, and the third rotation gives you here the skew, I would call it, the wing skew, where each of those profiles get some rotation with respect here to the root point, so to say, in the plane defined by the airfoil cross section itself. There are 2 other rotations which are not so natural, and you also see here not a real picture because it's actually a bit hard to depict. For example, the second value, you have some bend of the profile in this axis here. So it means this 2 profiles here will not be parallel to each other. And here the same holds there, where they will also not be parallel, but they will be simply in a different rotation axis. These 2 rotations are maybe more usable in combination with the translations here, or in combination with the bends. The bends are also a parameter which you can use while adding a wing, and the bending, I call it, is here given by 2 values. It's a bending out of the plane and it's a bending in the plane, so a bit similar to the rotation, but nevertheless a bit different. and here you simply can use an angle to produce also this kind of bending. And now you can think, of course, that if you here again apply also a rotation plus a bending, then it might make sense again to have both values here, or both transformation patterns separated. So this is the wing generator, and now we come to the rotor generator. You have already, I guess, an idea that basically now you can just simply combine wings to form a rotor. That's exactly what's happening. You define the number of wings, and again you have something like a rotor transformation. What is that? Well, I guess you assume already what that might be, and is correct. So you have basically a transformation applied to the entire rotor model, but now, and we will see it in a second, it's with respect to a different point. There are other two parameters like the hub parameters here. So what is the hub height, the hub diameter, and also the type here of the topping. Is it rounded, or is it like a tip here, like a pointy tip, or is there no topping at all? And like this you can automatically generate this hub model as well by using the rotor generator. So the transformation, as I said, is important. So the rotor transformation is actually applied to the base point of this cylinder here, which you can't really see. You have to be transparent. So the base point of the cylinder, the center point, is the root point for the rotor model. And then you have the wings added to the rotor, and then again each wing has the root point here, because this is simply taken from the wing assembly as we've seen before. That gives us the flexibility to make again or play around with these transformations. So you can, on the generation of the rotor, apply some transformation to the rotor itself. You can bring the entire rotor into a different coordinate system, but also you can play around with the wings itself, as you have seen before. And we have again these pictures here, which basically mean the same, and nevertheless I added them. So when you add the cross sections to a wing of the rotor, you can apply, of course, the transformations you have seen before, and like that generate something you see here with the translations of the rotations. Here you see actually a picture how what this rotation is doing here, as I have tried to describe before. And here you see it also more clearly how the rotation is applied in contrast to the other wings which have not got this transformation. And here you also see the flexibility, so it's possible to apply this transformation only to one of the wings, because we make here the possibility to add the profiles to each of the wings and applying transformations to each of them separately. And here you see again the bends. So this allows you to generate some nice rotor models, and we now have a look into the code itself for a second. I first want to, before I stop this presentation, point your interest also to one of our other softwares in the field of propeller design and propeller shape optimization. It's called Prop Design. It's actually a redesign of the kernel written by Anthony Falsone. You find here the link to his webpage and his awesome code. We took the code and packed it into some graphical user interface and some exchange to CAD systems and also to FEM programs, and thus it allows you to optimize with some semi-analytical computations the shape of a propeller for you, and then you can further use these models in a CAD or FEM process to produce or design the propeller. If you're interested in this, just write us an email here to this mail address. It will be also found in the comments under the video, and then you will be added to the mailing list. The software is not yet released. It will be released very soon, and then you can get the latest information. Enough with the presentation. Let's jump directly for a second into the Rhino models and model generators. As I said, this video is about the usage. There's another video about the installation. I will not go into detail again. Let's assume you managed to unpack this folder, which can be downloaded or checked out with SVN, and you managed to open your Rhino and managed to type in edit Python script to start the IDE. Let's start here from a zero script. And as I said before, the easiest way is really to have a look at some of the samples, and I will again take the sample number 3, which I also use in the installation guide for this Rhino. Actually, it's already the correct path. Let's use this sample number 3, and as I said before, you will have to wait a second. As I said before, you will have to adjust those lines 15, 16, 17 to make the code run directly, and this will be seen in the other video. So what comes now is usually that you have to make some imports. These are all imports pointing to our extension, and you can usually just copy those lines into your own script from the samples here. If there's something missing, run one of our models and see if there might be one of those imports missing, but usually this should be complete. What's happening now? In this model, let's maybe run it first. You see what happens. You see something is generated. Let's jump to Rhino and let's see in the rendered view what is generated. It's actually a wing model. You have 1, 2, 3, 4 airfoil cross sections, and you see they also have some relative displacements with respect to each other, so some rotations and translations. All this is happening in this script. So this is now starting from the wing generator. I could start now from the profile generator. I won't do it because actually you will see in the script that we also apply, of course, the profile generator. So here you define the origin point and the directions which will give you the basic transformation of the wing. This is the local coordinate system of the wing. It consists of a point, which is the root point of the first airfoil cross section, and some plane or some directions to define a plane. This is the transformation which will be used in this line here to be passed to the constructor of the wing generator. So the wing length is 400 with respect to the units you have in your drawing, and then you have a wing model with this wing generator, and this inherits automatically then the transformation defined here. Now you start adding, in this case, 4 airfoil cross sections. So here you actually use then the airfoil generator, the NACA generator for airfoil cross sections. Here a 4-digit series, and here in the init you pass the parameters of chord length and thickness ratio, which I showed in the presentation, and you do this 4 times. So here you only generate those cross sections, but then you also add them to the wing model. This happens here. So here you call this add profile, which I mentioned before, this add profile member function of the wing generator, and add one of the profiles to this model. And the first one you add, of course, at the root point of the wing. You could also do it somewhere else, but let's assume it makes sense to add it at the root point of the wing. And the second, third and fourth one, of course, you add with a rotation and translation vector. The rotation vector could be 0 if you don't pass it. You could also add a bend here, so you see the bend is not passed. The rotation could be also left out, and then you simply don't pass it and then assume there is no relative rotation assumed for this certain profile which I've added now. But what should be always added is here the third value. As I said, this one defines the longitudinal position of the wing model. So we could, for example, here say we have no local rotations, and actually these ones here, they should be actually 0, so we don't want to have any kind of translations except the third one. So this one is the important one on the longitudinal direction of the wing, but the other two which you saw on the slides, which are something like in plane and out of plane translations, they should be 0. And if I didn't make a mistake now, no I did not, you will see here that this model here which is generated is similar to this one, with the difference that you don't have applied any kind of rotations and translations. You see there's some translations going out of the model, and you see some rotations like a skew. So this is basically how you generate a wing. If you look, for example, into the number 4, I think it should be. Let's have a look at that. It's a more complicated model. If you go to the samples, you also see here a PDF, and in this PDF you see an overview. So number 4 is actually something like a turbine, a wind turbine blade, and I will not run it now. I will just want to show you that here we do basically the same steps. We generate a wing, and then we basically add the wing cross sections. But now we don't do them like before, that we make them hard coded and add them, but we make it in a loop. That makes sense, of course. So we have a number of profiles we want to add, 50 for example, and then of course, as I said, you can define the X position here along the wing, and then we add some of the profiles, and the profiles are here, for example, changed. So depending on the position on the longitudinal direction, you have, for example, at the beginning a circle, then later you have a 4-digit series, and then you have another 4-digit series. And also you can use some functions which define how the, for example, rotations or translations are given. Let's assume, for example, you have a linear change of the translation with respect to the longitudinal direction. It's easy to make a Python function for that. We provide you with some templates which you can have a look at, but it's easy to write also your own functions and use them to define the translations with respect to the position along the longitudinal direction of the wing, which is the most natural way to describe it. And if you use this kind of methods also in the rotor model, you can generate something like the model 8 or the model 9, for example. Let's have a look at the model 9. So the difference is now that we don't use the wing generator, but we use the rotor generator. But you see it's just hierarchically seen the next logical step. So here you basically use the rotor generator, not the wing generator. But the same, you have a local transformation, and now you have different parameters like the rotor radius, the number of wings, and some parameters for the hub shape. And then the next step is to add the wings, and each wing can have a transformation itself. That's important. And then you add here in a double loop, you run over the number of wings and you run over the number of profiles within each wing, and you add them here again to the wing model, and the wing model is the wing within the rotor, and again you can apply your local transformations. You see it's rather a short script, and nevertheless it allows you to generate a nice model. I will actually show you. I will delete this one here and basically run the model. The only thing I have to do is to copy those lines here to make the extension known, as I explained in the other video. And if I do so, you will see that the model will be generated. You see it can be a process taking a bit of a time, depending especially how many profiles you add to the wing model. But if you succeeded, and it will be done in a second, you see that you can, with a few lines and with those utilities you provide, generate some rather complicated structures. So still have to wait a second and now jump to the model itself. Sorry for the delay here. Now you see it's quite a model where probably you added a little bit too many profiles here. The performance is not the best, but you see here you can generate something more complex with rather a few lines of code. This is what the extension should do for you, and I hope you have fun doing that. We appreciate to be cited if you use this extension in a commercial way or for academia, and thank you very much for your attention. Goodbye.